part in the online chat, but I don't know if that's happened yet. Okay. You might want to just scroll up. Sorry.
Oh yeah. Yeah, now.
Yeah, John, did you share that here in the Teams chat?
Yeah, that did. You might have to do it in the Q&A rather than chat.
I don't think you can do it in chat. I think Q&A, you do
Chat stuff.
It says Q&A. So,
Like question. Just put that.
you can perhaps pin it. It's is the same.
Then brilliant. Thumbs up. So the practical for those online should be shared and pinned at the top of the Q&A. Right, brilliant. So just to get on to practical class, then this is a GitHub Jupyter notebook, it's a binder. So I think you're used to that now. It's developed by one of my PhD students, Andrew Watson, a few years ago. Looking at doing the forward modelling for this. And what we're trying to do is get these parameters. Where is it? X, Y. Strike dip break I mentioned. How much is moved?
Yeah, we've lost the sound.
Oh, right. Apparently. I won't do that bit.
Is it on?
It says it's got, I mean, it looks like it's got me when I speak. Is that the right one?
Yeah, that's all right.
Yeah.
That's fine then.
So we're trying to get those source parameters. And then, as I said, the rate is the hard one. The normal fault is minus 90. A reverse fault is plus 90. Left lateral 0, right lateral 180. So just ask us if that particular bit gets a bit confusing. So just remember, in picture form, fault plane through limestone and colluvium in Greece. 3.5 is quite steep, 60 odd degrees, the dip relative to the horizontal of the fault plane. And then this is that fault plane with peak of the scale at the bottom. Looking onto the fault plane, so it looks like a cliff, but it's not quite a vertical cliff, but it's a steep cliff. If you imagine that colluvial soil on top, what the earthquake is doing in each event every few hundred or thousand years is it slips suddenly in the earthquake. It's basically dragging on this fault plane and it causes striations on it. So you're scratching all the pebbles here, like 10 pebbles, on there and create striations in the fault, natural rake. So this is a normal faulting earthquake. This side's gone down the hang with respect to the football. So that have a rake of minus 90 if it's pure normal, so it's just off that, it's about minus 70. So that's that. And then the strike in this case was east-west, so that would be a strike of 90. So what we want you to do is change those parameters here. John will go over this now. The parameters, the numbers you'll change, it explains what they are here. It sets up the model, does the dislocation, that card dislocation, displacement, and gives you these pictures. How much does it move east-west, which we're not measuring? How much moves north-south, which you're not measuring, and how much is moving vertical, which you're not measuring? It's those three components projected into the line of sight. But they basically give you this three-dimensional plot. So that's what you'd want to know happened in the Earth, but we actually get the line of sight displacements. So they're projected using simple trigonometry into the line of sight. So it looks like this, the displacement all together added up, projected in line of sight, and this is the rough fringes, contours. They're a bit easier to interpret the shape of these and the extra loads you get around the edge than it is just this displacement. And we'll do that for a few earthquakes that John will go through now. There was 2021 Greece earthquake, magnitude 6.3, an Afghanistan earthquake, magnitude 5.9, so towards that smaller end, with a lot of noise data, see there. And then also another one from Iran in 2017, really quite a large earthquake. So I think that's all of them. John, would you like to take it? John's the one that's doing sort of semi-automated automatic earthquake detector and modeler system. That's what he's been doing for his PhD. Trying to capture as many of those earthquakes in the portal that we provide. So thanks, John.
Sure. So first of all, has everyone got the Jupyter notebook up and ready to go? It should be in the chat if you've not got it. So I'll do the same eventually. Okay, so as John said, we're just going to be running through. The idea of this is we've got some interferograms, we've got a model, we're going to try and fit the interferogram to the model, and then we know what the earthquake looked like. So I'm going to just like quick show of hands, how many people actually look at earthquakes for their PhD or work or whatever you're doing? Okay, we've got a few. So I'll ask you guys, because John's very quickly just run through 9 different source parameters, and it can get confusing. I would ask the earthquake people in the room to help the non-earthquake people in the room, because otherwise it can get a bit confusing. Okay. The other thing I'd like to say as well is that it's quite fun to do this collaboratively. The idea is to get the best model possible to the interferogram. So if you want to just go around, work together in groups, see if you can get as small a residual as possible. So we're going to minus the interferogram and the model, and if we get nothing left, when we know we've got a pretty good model, well, there should be some noise left, apart from one. So first of all, run through running so we're just going to import some modules, and then the first thing we're going to do is run a synthetic. So this is the model that we have. What we're doing is we've got a rectangular fault plane that is shifting at depth. It's got those 9 fault parameters: the rake, slip, X, Y, where it is, the rake, sort of which direction the plane is moving relative to the other plane. We've got the strike, which is essentially just a line it makes at the surface, like that, sorry. Then we've got the dip, which is the angle the plane is making with the surface. So all of these we can adjust, and it'll have an impact on the model, and we'll have to try and fit that to the interferogram. The other thing we have is the amount of slip. So how much is this plane moving relative to the other one? So that's usually in sort of meters, and then we have depth. So this is all happening not at the surface, it's happening at depth. And what we're seeing is the surface projection of the deformation of that rectangular plane moving at depth. Quite a complicated model. Well, it's not. It's an analytical model, but it has a lot of parameters. There's a lot of things to play with. It's a lot easier to do it in an inversion where it just does more volume. But if you don't understand what you're actually fitting, you don't understand your results. So, first of all, we're going to look at the model that we're going to be using. So this is what our Ricardo model is generating. But what we get is the east-west displacement, the north-south displacement, and we get the vertical displacement. So we've got stuff moving east-west, we've got stuff moving north-south, and we've got it going either up or down. And then what we actually see is a sort of convolution of all 3 of those, and that's what our displacement looks like on the surface. Now, the important thing to note is because of the how InSAR satellites work, or polar orbiting InSAR satellites work, we have very little sensitivity to north-south. So we only have a incident angle of sort of 10 degrees or 170 degrees if you're doing ascending or descending. And it's only because we're not doing directly north-south motion that we get any, it's only because we're not going sort of round the, straight over the pole that we get any sensitivity to north-south. So first of all, what I wanted to try and do is you've got the parameters at the top. All 9 of the parameters, there is 9, isn't there? 1, 2, 3, 4, 5, 6, 7, 8, 9. I did do this beforehand. And what we want to do is just start adjusting those and see what we get in our east displacement, in our north displacement, and in our vertical displacement. The sort of way this works is you have sensitivity to sort of 10% north-south, you have 70% east-west, and then you have 90% to vertical displacement. So it's the vertical displacement that's dominating. So that's the one to sort of really get your eye into. At the moment, this is, I believe, where are we going? So we're going towards the east, and that's going towards the west. So we've got a left lateral strike slip fault at the moment, but sort of I'm really relying on the earthquake people in the room here to help out those that don't know how to produce a thrust fault or a normal fault. But just start playing around, and you can see what these surface deformations should look like. So I'll give you sort of 10 minutes to work through that, and yeah, try and get a feel for it, what the model is actually doing. Okay, hang on. So this is a strike slip fault. So you've got the thing going sort of like that, and then if you go to the next block of code, you've got a dip slip fault. So you can get an idea of how the different fault mechanisms might work. So yeah, have a go with adjusting the depth, adjusting the location, adjusting the slip, and you'll see that the sort of wavelength of the deformation will change, the magnitude of the deformation will change, and the radiation pattern will change as well. And that'll help you when you start to try and fit to real data. So yeah, have a play. You got sort of 10 minutes. It also, if anyone has any questions throughout, please just grab me and I can. There's Benji in the room as well, and John, who's probably a lot better at this than the two of us. So if you get John, he'll probably help you. How long have I got for this, John?
About half an hour but you can do a little bit more, so a coffee break after this.
Okay, perfect. I'll try not to eat into your coffee break.
If you do about 10 minutes,
yeah. Okay. Okay. Well, in that case, yeah. Okay, so I'm gonna do the next block of code as well, just so you can kind of understand what we're aiming for. So what we see in the next block of code is all of this model projected into the line of sight of the satellite. So the satellite's right looking, it's going north-south, and we only have one look direction. So all the satellite sees is something moving towards the satellite or away from the satellite. So that's all we can actually produce. But our forward model, we can say, what's the north-south motion, what's the east-west motion, what's up-down, but we need to make sure we're like basically emulating what the satellite can see. So that's what this next bit of code is doing. And you can start to think your synthetics where you've been playing around with east-west, north-south motion, what does the satellite actually see? And this is what we'll be fitting to the data. So this is the kind of, this is the important bit, and this is what you'll be able to see when you're when you're running this yourself. But it's, yeah, it's there's all types of motion in here, but as I said, the satellite's only sensitive to like vertical, east-west, and then we get a bit north. So have a look what it looks like in your satellite line of sight and see if you can make a funky pattern and what that's actually doing. Are there any questions online?
There's someone asking. They have this body.
What? Yeah, just show me.
We've got questions about, well, we've got one about GBIS, but that we answer later. We've got this one that's actually kind of related.
Okay, so they're kind of related to each other. So for the question online is, in the real world, how do we get fault parameters so that we can model the displacement like the rake and the dip? So there's a few ways. You can go to a seismic catalog and try and get the seismic focal mechanisms. Those won't, well, what I've found during the course of my research is that those won't directly match to the INSAR inverted source parameters. But what you can do, which is the sort of next question, is you could do a Bayesian inversion. So there's a piece of software called GBIS, which is the geodetic Bayesian inversion software. And what this does is it does Bayesian inference for all the different parameters and tries to do an inversion to fit your model to the data. So what we're doing in the room and online is like a collective inversion. So rather than doing it in a Bayesian manner, we're doing it sort of feeding it to a room of 100 people and hoping that we get a solution. But there are smarter ways of doing it. If you just need like a starting point, I would suggest going to Seismic Catalog. So for the person asking about GBIS, the GBIS codes on the Comet website is not updated regularly. It does work, and it is the base one. It's version 2 at the moment. There are people that have been working on GBIS and adding to it, and the best person to sort of email would be either me or John or anyone at Leeds, really. There isn't a webinar or a course on GBIS as far as I'm aware, but stay tuned. I'm trying to write a Python version at the moment, so you might not have to use MATLAB. But yeah, if you want to email me, I'll leave my details here, and I can help out with any GBIS queries.
Okay, so it's in the previous bit.
Yeah. Okay. Cool. Okay. So everyone got their eye in a bit, knows what they're looking at, knows what the satellite's looking at. Feeling good? I'm going to take that as a yes. Okay, so the first thing we're going to do now is the next bit of code. We're going to be loading in some actual data. So on the left, we have the unwrapped version, which is the sort of actual displacement that the satellite is seeing. So the first thing to know to sort of talk about is that anything positive is moving away from the satellite. So it's important to think about sort of like what's the direction of. Is there a whiteboard here? No. Okay.
There.
That's not okay. So it's a right-looking satellite. If we're going ascending, we're at -10 degrees. So call that pole, and we've got a right-looking satellite. So you've got to try and think about, okay, so if something moves up, what does that look like to the satellite? It looks positive. Sorry, it looks negative. Anything away from the satellite is positive. If something moves down, so like that, we're getting further away from this arrow, so we're going to be positive. Okay, so things moving down, positive, things moving up, negative. But then we've also got sensitivity to east-west. So you need to think about how any motion on the ground is going to look to basically that vector. So we've loaded in some data. We've got the unwrapped, which is our actual displacement, and then we've got the wrapped, which is what the satellite is measuring. Essentially, you've got your phase change. So what have we got here? We've got something that is moving away from the satellite here, and then we've got a slight negative bulge here, so it's moving towards the satellite. Does this look like either of the two synthetics that we were playing around with? I'm going to answer for you. It does. It looks like this one. So what we know is we've got, so it's quite characteristic of a dip slip event here. We've got two loads. The fault plane is probably somewhere here. We've got a lot of displacement on this side, and we've got very little displacement on here. And what that means is if it's going, where's that? Yes, sir.
Why is it a dip slip if the bit that looks like it's moving looks like it's going
towards the satellite? Okay, it's the characteristic two lobes basically is our dip slip. It's also because this is going, so it's going away from the satellite, which means it's going down. So we've got a large amount of downwards displacement here, and then we've got like a small amount of uplift here, which is kind of characteristic of a normal fault. So you've got something that's just moving away.
Scale says forward, so that it, I guess I was expecting to say minus one.
Yeah. No, it's because it's It's that's the thing to think about. It's the line of sight. So away from satellite is positive. Yeah. It is confusing, but it is just a conventional. It's whichever one you pick, and it's something to really be like find out which convention people are using because people use different ones, and yeah, it can go wrong.
And mixed class is the other way.
Is it?
Yeah.
Hang on, let me double check that this is the way that Andrew's done it. Range increase is positive. Yeah. Okay.
GBIS is opposite to mixed class, which is helpful.
Yeah. Just make sure you know what the convention is when you're doing. Okay. So next we've got our own model here once it loads. Okay. So what we're showing here is where we're putting the fault plane, and this is our model. Doesn't look particularly like the data. And this is our residual. So we know we've got way too much uplift coming over on this side. So we've added to the uplift on this side, and we've basically not done anything to the substance. So this is what's left when you subtract the two. So what we want to do is try and get this to look as much like this as possible. And we're just going to do a matching technique. The first thing I would say is it looks like the fault plane is kind of in the wrong place. I would say that a 90-degree dip, something that's going straight down, we know it probably should be normal faulting. It's probably not normal faulting vertically, so the dip needs adjusting. And I would say that the slip actually seems somewhat reasonable. And then I would say the rake will need adjusting. We've got a strike slip there, so the rake is how one plane is moving relative to the other. If you've got naught, you've got it moving basically like that. And we think this is probably a normal fault. So you need to think about which direction that plane should be moving relative to this one. I'll give you a clue. It's around 90 degrees, minus 90. But minus 90 or 90? Minus 90.
Yeah, 270.
Or 270. Yeah. Okay, so I've got the actual answers here provided by John, and like they're pretty close. I think the actual real inversion gets pretty close to what John did. So yes, yeah. So that's usually use that as the starting point. So you know that the moment tensors are going to be pretty close. The seismic moments, like they're not exactly the same, just because the seismic inversion is sort of it's measuring a different thing, right? So they're usually pretty close. My work at the beginning of my PhD shows that they can be really not that close, but they're a good starting point. And it's whether the INSAR or the seismology is correct is kind of it's up in the air. But yeah, it's a good starting point. So yeah, play around with that. At random intervals, I'm going to ask you all to tell me what your RMS is, and we'll write the best RMS on the board and put it in here, and I'll see what the best model we can come up with is. So please. Okay, if I mute this screen, they can still see it online, right? Okay. Fine. It's all right. I'll try my own. I'll do it without looking at John's to begin with. See how close I can get. Let's go. Again, if you've got any questions, just stick your hand up, someone will get to you. Okay. What's everyone's RMS looking like? So if I've got 21.42 millimeters, which is not brilliant. Anyone done better? No? Okay, I'm going to start having a look. I'm going to come look at your models.
You like a game show, like we've got 23 in here. Exactly. Yeah, sarcastic.
I've got the most, it's got the highest.
That's a neat. That's 16. So it's Steve got the very yeah. I've changed that. So it's doing. It's doing that. But it should go that. Yeah, minus. Otherwise, it's going. Okay. That's right, yeah. They follow the so first. Yeah. So it's like three dimensions, two dimensions, three dimensions, and what yeah. Yeah, basically. I think yeah. And that little code, then 7,000. That was a US chess study. So if you look at that in the US chess, you can see. Yeah. Yeah. There's just this place. Otherwise, it's perfect. Goes to the US chess, gets their allocation, and then it clips a small area. And it's, yeah, range around. So if you could, this website, yeah. So this is as the all of the frames that you so if your area if your area is covered by frames, then so it's they should be processed for one time. So you can go into our database. So it's that shows that's the big data. It's big data. So
I'm going to move on now. You'll have fun with a normal fault. So this is an easy one. We're going to be moving on to a hard one. Lots of noise. So first of all, anyone brave enough to share their RMS? 4.3. That's not bad. It's good. Yeah, nice. Can you give me your model practice, or is that too much?
So I didn't change the center.
Okay.
30 minus 95.
Minus 95. and then slip knot. Oh, not 10. That's going to be big. Yeah, nice. So I would say that your dip is slightly too shallow. So this lobe here is too small. Yeah, and then you've not quite fit this lobe. So you need to sort of either make the depth bigger to make it a longer wavelength signal to try and fit that. And then if you're deeper, the surface is going to have less uplift. So you need to accommodate that with extra slip, basically. But yeah, it's good. It's a good effort. Anyone else want to share? 18.
On 89 sounds like.
Okay.
So just change to minus 83 of break.
Let's have a look.
No, I have something. To go way more.
Yeah, well, I've changed the location and that's all I've changed. Oh, and the width.
And the week stay.
Okay. Are these noughts on yours?
And sleeve is 1.3.
Ah, 22. Still, that's better than I was getting.
Excuse me.
Yep.
We use research for, finding the optimal parameters.
Yeah. So that's what essentially GBIS does, but it does it with Bayesian inference so that you get all the different trade-offs of each. So you get the full probability distribution of posterior distribution, sorry, of each of the parameters. So it's essentially GBIS is doing a clever way of doing that, and I'm doing a manual grid search by getting all of you guys to do it. That's kind of the idea. Okay, so we'll move on to Afghanistan. So this, you see these four lobes here. That's characteristic of a strike slip event. So if I go back to this here, you can see the vertical displacement gives us these four lobes. So obviously it's moving up here. It's moving, where's it going? Go west to east? No, east to west. So it's going like that. So you've got obvious motion in your east-west. The north-south displacement, basically what's happening is you're sucking in material from here and depositing it here. So you end up with this one going south, this one going north, and then vice versa the other way around. And that's the same with the vertical displacement. As you kind of pull material in from one side, you deposit it on the other side. So you get slight uplifts at the corner of the fault plane, and the same way on the other side. So that's where you end up with sort of these four characteristic lobes for a strike slip, and you end up with two lobes for a dip slip. So if you see something that looks like this, you can be relatively confident you've got a strike slip event. You can also look at the regional setting, the context of the earthquake, and try and get your eye in that way. But if we load that in, we're going to do the same thing again. I would say this one's is slightly bigger. So look at the magnitude of it. So it's a lot smaller, sorry. So look at the magnitude of it, what you want your slip and your depth to be. So the magnitude is dictated by the length and width of the fault plane that's rupturing, plus the amount it's moving. So if you want it to be bigger, change the length, the width, and the slip. And you can kind of tell where the strike of this event should be, because you want four lobes on each side. You want a line through the middle of it. So you can tell for this one, I would start with the strike looking a little bit iffy, and then start playing around with your depth and your actual fault location. So this one is significantly harder. Strike slips always are. Would be mine. And the other thing to notice here as well, sorry, is that we've got a descending track. So this time our vector is looking like this being our look direction. I say that's a lot more than 10 degrees. This is our look vector. So anything moving up is going towards the satellite, but it changes east-west. So you need to sort of get your head into where that vector's looking. And yeah, but it shouldn't make a huge amount of difference for this one, I think. Okay. Okay, how's everyone? How's everyone getting on? Lowest RMS? Anyone care to share an RMS?
20.88.
20.88. Oh, that was very good. Yeah. I mean, well, very good. It's better than mine. What parameters have you gone for?
8.0, 9.0, 1.0.
Yeah.
Put it straight to your 5.
Yeah.
Then the 17.
Okay.
1.5 and then B to 15. So Select the 1.2.
Yep.
Height is 8.5. Width is 5 meters deep. Length 10 meters deep.
Okay. That'll work. Yeah. Nice. So how do we prove that? It's looking good. I think the dip is slightly too dipped because we've got some residual coming through on this side. We're missing one of the lobes there. Let's have a look at it. I didn't check what it was before. Yeah. Managed to make it worse by 0.01 millimeters. So it's pretty good. Okay. If you've got, I mean, feel free to go back to the other one as well and see if you can do better. How long have we got left, John? What is it?
0.
0 minutes. Okay, perfect. Okay, so the final one is a mess, and but it's a thrust bolt. So what you've got here is you've got one plane being forced up on top of the other one, and you get this sort of characteristic two-lobe pattern. But because it's so large, it's going to be hard. It's very noisy. But as we are at 0 minutes, I'll let you guys do that one throughout the coffee break or in your own time or whenever you'd like to. So all of this code is available on the GitHub. The library is there. There's a very nice implementation of the Arcada forward model, which is really nice to use. And there's a lot of helpful functions in the library for the practical. So if you can, go and have a look at the code, actually dig into it yourself. And then the next thing to do, if you're interested in following this further, is rather than fitting it yourself, is use GBIS and start seeing what that's all about. And that's how you would do it, sort of with a practical application. But yeah, hopefully you've all kind of got your eye in a bit. And yeah, so have a play, grab a copy whilst you have a play. But yeah, you can finish the thrust bolt on your own time. Yeah.
So you were saying that when you match these, you get different answers sometimes, like what you get from the